oxygen, and I got some product called magnesium oxide. Okay, and so what ended up happening is that when I added two things together, so I can be safe. Let's try some safety. Safety first, kids. You might be here half an hour waiting for this thing to burn. Okay, so as you can see, I'm combining. This is a reaction where I'm combining two things together. I'm combining magnesium with oxygen. And we're getting there. There we go. And so at the end, you get magnesium oxide. Now, if you look on your evidences of a reaction, can somebody raise their hand and tell me one that they saw here that let me know that a chemical reaction occurred?
Production of heat and light.
Yes, that. Thank you for raising your hand.
That wasn't the one I was going to say, though.
Yes. So you can see that there was a reaction because there was a production of both heat and light. There's another one on there too.
Evolution of a gas.
Was there a gas?
Yeah, like coming off of it, like smoke or something.
That was oxygen. Pure oxygen, just adding it. Yeah. There was no evolution of a gas. You'll see why. But there was a color change maybe. What is that? It's white. And was it white when I started with it?
No.
No, it was a silvery color. Okay? So, those are two things that you can see happen because a reaction takes place. There was a color change, there was heat, there was light. Those are evidences of some type of chemical reaction. Okay? We're going to be getting into labs sometime this week and next week so that we can start beginning to see what's going on with these reactions, why we're producing some type of chemical reaction. Okay? Another one. I'm going to take this lovely little liquid right here, hydrochloric acid. Okay, and so what I'm doing is I'm going to take a magnesium ribbon and I'm going to perform another reaction. Okay, I'm going to take magnesium and I'm going to add it to my hydrochloric acid, and based on some stuff that I know on reactions that you'll eventually know, I'm going to end up with magnesium chloride and hydrogen. Okay, is hydrogen a nonmetal?
Yeah.
It is? Okay, what kind of nonmetal is it? What happens? It's a gas. Is it a gas? Okay, so let's watch what happens. Okay?
Nothing.
No, something's happening.
Fizzing.
It's fizzing. Is that maybe an evidence of a chemical reaction?
Yeah.
Yes, what else? Can you see some gas coming out of there now? There's a little bit of one. That's hydrogen gas that's being giving off. So, the evolution of a gas, some bubbling and some fizzing, another reaction. Evidence that a reaction is taking place. So what's happening is that my magnesium is bonding with my chlorine, and so because it's bonding with my chlorine, hydrogen has nowhere to go except in gaseous form out of my solution. So that's what happens when I mix magnesium with hydrochloric acid. This is a reaction, okay? And eventually what's going to happen is this little piece of magnesium is eventually going to go away. It's not going to be in solid form anymore. It's going to have bonded with all these different chlorine atoms and created magnesium chloride. Okay? So, you can see there's like 3, 4, 5 different ways that we can show evidence of a chemical reaction. That's what AP wants you to know. How can we predict what's going to happen? How do we know a chemical reaction is actually taking place? Okay? So that's what we're going to talk about as we get into this stuff. And so look at your notes underneath Roman numeral 2. Understanding parts of a chemical reaction. Okay? You know about chemical reactions. You just don't know that you know. Okay? So we're going to start looking at chemical reactions and identifying all the parts of the reaction. Okay? So I'm going to write this one on the board, the big one that we've got on our notes page, and we're going to work with this and talk about why this reaction is like it is. We're going to talk about each of the individual parts of the reaction, and that's going to kind of get us familiar with all the terminology that we need. Okay, so as I'm writing this up here, let's answer question number 1. Question number 1 underneath there. It says list the reactants, okay? Everything on this side of my arrow, this side over here, are going to be my reactants. Okay? So everything on the left-hand side of a chemical equation is a reactant. It's what I'm putting in to my equation. It's what I'm mixing together and combining at the beginning of my reaction. Okay, so we have NaCl H2SO4, and MnO2. Those are my three reactants in this formula. My three reactants. Okay? Everything on the right-hand side of my arrow is going to be my product. It's what I get out of the reaction once I combine all of my reactants together. Okay, so you're going to list those four products there. You've got Na2SO4, MnCl2, H2O, and Cl2. Okay? Those are your products. So make sure you know the difference between a reactant and a product. What I put in, what I get out. Okay, number 3. There are 4 different types of things that you can put into a solution. Number 3, list the solids. Okay, if you look next to every single one of these compounds in there, there's something that is in parentheses. That tells me what state my compound is in. Okay, so if you see an S in parentheses, you know that that compound is a solid. It's not going to dissolve in the water or my solution. Okay, so what's the solid going to be? What letter is it going to be? Letter C, that's manganese 4 oxide. Okay, so that's your solid in this compound, MnO2, manganese 4 oxide. That's the solid in this reaction. Okay, number 4 says list the gases. It's going to have a letter G next to it in parentheses. So where's my gas? Yep, Cl2, chlorine. If you remember, we said that salt is a mixture of sodium, which is a metal, and chlorine, which is a poisonous gas. Chlorine's a gas. Okay, number 5 says list the liquids. What's going to be my liquid in this solution? H2O. There's going to be an L next to it. H2O. So at the end of my solution, at the end, my products, water is in liquid form, is what's going to come out of this. When I mix all those together, one of my products is going to be water in liquid form. Okay, and then number 6. Number 6, a new term for you. Okay, list the aqueous solutions. Aqueous. That means that my compound is dissolvable in water. So it does not matter what state it's in, it's going to be dissolved in water. So if I have something that's going to be dissolved in water, it's called aqueous. So NaCl is aqueous. Remember we talked about that? If I put salt in water and I mix it around, the salt gets dissolved because of the polarity. We talked about that. Okay, this is sulfuric acid. It's aqueous. And if you look under, there's 2 more. Sodium sulfate. And what's the other one? Manganese 2 chloride. Okay, those are your 4 aqueous compounds. Those are your 4 aqueous compounds. Okay, any questions so far? Okay, that's kind of your intro to solutions. Intro to products, reactants, creating a solution, creating some type of chemical reaction. Now we're actually going to start talking about this. What does all of this mean? How do we fix all of this and make it chemically right? Okay? Who knows what a mole is? Anybody heard the term mole?
Not in this context.
Ooh, not in this context. Not the kind of mole that like lives underground. How about a chemistry mold? Okay, here's what I want you to do. Everybody take your phone out, look up the definition of a chemical mold. Look it up. It's easier for you to learn it without me looking at you and speaking it to you. Look up a mold. When somebody's got a good definition, one that we can all understand, let me hear it. Look up a mold. Let's hear it, Nora. You got a good definition?
It's a unit of measurement.
Okay, I need more than that. A little bit more than that.
And it's like
Gosh. It is a unit of measurement, that is correct.
for amounts of chemical substances.
Yeah, for amount of a substance. So that means how much of this do I have? Or this, or any one of these other products or reactants. How much of that do I have? Okay? Now, here's where balancing reactions comes into play. Okay? We're going to have to balance everything in chemistry. Has anybody ever heard of the law of conservation of mass? Law of conservation of mass means whatever we start with, we have to get the same amount of mass at the end. So when I have a chemical reaction, however many sodium atoms I have at the beginning, I've got to have the same amount at the end. However many sulfur and oxygen and chlorine and hydrogen I've got to get out at the end as well. That's the law of conservation of mass. So how do we do that? We have to balance equations. We have to balance equations, okay? So here's how we're going to start this.
I remember utterly failing balancing.
Oh, you're not going to fail anymore, because we're going to teach it right, okay? So, here's what you're going to do. Anytime you see a chemical reaction, you have to balance it. And here's how we'll do it. First, you're going to look at your reactant side, and you're going to write every element that we have on this side. Okay, so we have some sodium, we've got some chlorine, we've got hydrogen, we've got sulfur, we've got oxygen, and we've got manganese. Okay, so we know all of those elements are in the reactants, which also means they're going to have to be where? In the products. So I'm going to write Na, NCl, NH, SO, and Mn. Okay, now, we have to look at every equation we see to make sure it's balanced. Okay? Is this equation balanced? Do we have the same amount of everything as a reactant as we do a product over here? No? Is it no? Do we have the same amount of sodium on the left-hand side as we do as the right-hand side? No. So we know that this equation is not balanced. So according to the law of conservation of mass, we have to balance this. Well, how in the heck are we going to balance this? You notice I put little blanks in front of all of these different compounds. All of those blanks are going to be spots for what's called a coefficient. It's a whole number that comes in front of something. Okay? So what we're going to do is we're going to place whole numbers in front of all these different compounds to try and balance this formula out. That's where a mole comes in. Right now I've got 1 mole of NaCl. It means I've got like 1 molecule of NaCl and 1 mole of H2SO4 and 1 mole of manganese 4 oxide and so on and so on. Now I'm going to change these coefficients to increase or decrease the number of moles so I can balance everything out. Okay, so what we're going to do is we're going to tell ourselves how many of each of these we have here. How many sodium do we have on the left-hand side? 1. Write a 1. How many chlorine do I have? 1. How many hydrogen? 2. I've got a subscript 2 here. How many sulfur? 1. How many oxygen? 6. 6. 4 here and 2 here. And then how many manganese? 1. Okay, so that's where I started with. Now, I've got to go to my products, and I've got to figure out how many of each I have up here. How many sodium do I have on this side? 2. How many chlorine do I have? 4. That's where it's easy to get tripped up. How many hydrogen?
2.
How many sulfur? 1. How many oxygen? 5. And how many manganese? So, right now, as I sit, I've got hydrogen balanced, and sulfur balanced, and manganese balanced. Okay, so what you're going to do at this point is try and balance this equation by putting whole number coefficients in front to try and balance this out. Now, this one is kind of difficult. I want you to see the process of some of these and how long it can take you, but the process of how it works, okay? So, let's try and balance out something easy first. Okay, what's easy looking to balance out? Maybe sodium? We'll start with sodium. Let's look at sodium. Can we balance sodium out here? Well, we got to follow the process. It's going to take some time. Okay, so let's balance out sodium. What can we do to balance out sodium on both sides? We can put a 2 as a coefficient here. Let's do that. Let's put a 2 as a coefficient here. Okay, so that gets my sodium balanced out. Yay! And I changed my chlorine. I've now got 2 chlorine. But is my chlorine balanced out? No. So I know I'm probably going to have to change this again, right? Okay, so we can either keep moving or we can change it now. I say we change it now. That's easier to do. So we know that we're going to have 4 chlorine at some point, right? So let's go ahead and change that to a 4. Okay, so that's going to unbalance my sodium, unfortunately, but sometimes you have to do that to make these things work. So now I've got 4 sodium and 4 chlorine. So now my chlorine is balanced out, right? Okay, so let's move on. What can we try and balance out that looks kind of easy here? Well, we got 2 things, sodium and oxygen. Which one would you rather try to attack? Sodium looks a lot easier, 2 and 4, instead of balancing out a 5 and a 6, that's hard. So what can we do to get sodium balanced on this right-hand side? We can put a 2 right here for my sodium sulfate. Let's do that. Okay, so if I put a 2 there, it distributes out to everything in my compound. So now, how many sodium do I have? I've got Na2, so it's going to be 2 times 2, which gives me 4. That balances my sodium out. Okay, but again, the 2 distributes out to the whole thing. How many sulfur do I now have? 2, 2 sulfur. So my sulfur's not balanced out anymore. Okay, how many oxygen do I now have?
9.
I've got 8 right here, plus 1 right there, which gives me 9. Okay? So now we've still got 4 elements that are balanced out. What's going to be the easier one to attack? We've got oxygen with 6 and 9, sulfur with 1 and 2. I say we try to do the sulfur. That looks easier, right? So how do we balance the sulfur out here? Add a 2 to where? The H2SO4, your sulfuric acid, okay? I like that. So, what do we do to our hydrogen here? How many hydrogen do we now have? 4. Okay, so hydrogen's no longer balanced, but that's okay, because it's going to work out great. Okay, how many sulfur do we now have? 2. So now sulfur's back balanced. And how many oxygen do I have? 2 times 4 gives me 8, plus my 2 over here gives me 10 total. Okay, now, we've got 10 oxygen and 9 oxygen, 4 hydrogen and 2 hydrogen. Maybe it's easier to balance out the hydrogen, so let's look and see if we can balance out hydrogen. Okay, so what are we going to do? How can we balance out hydrogen on this side?
2 H2O.
We put a 2 in front of the H2O, let's do that. Okay, so how many hydrogen do I now have? 4? So are my hydrogens balanced? Yeah. And what about my oxygen? Okay, well, I had 8 oxygen here. How many oxygen do I now have here? 2 more, so 8 plus 2 gives me... Am I balanced?
Wait, no, you had 9 there.
Yeah, now it's 10, right? It was 9 before I put a 2 there.
Hold on, but 2 times oxygen means 2 oxygens. 9 plus 2 is 11.
It's not 9 plus 2. How many oxygen do I have here?
It's 8.
How many do I have here?
It's 2, but why was there 9 there?
Because there were 9 oxygens before I put a coefficient of 2 here, right?
Because there's 8 there.
Right, because there was, if I take this 2 away, how many oxygens do I have up here? 8 plus 1, right?
So why don't you not 8 plus 2?
Hmm?
Why don't you multiply?
You do. 2 times 1.
Yeah, I'm trying to add it. So.
This number tells me how many oxygens I have here. I'm not multiplying by anything right here.
Oh, okay.
Yeah. Okay, so I put a 2 here. Now how many oxygens do I have? 10. 8 plus 2 gives me my 10. So am I balanced? Am I stable? Is everybody full and happy and wanting to react? Yes, okay.
What about the sulfur on the right side?
What about it? I see 2 of them. Yeah. 2. Okay, so now, everybody is balanced. I'm following the law of conservation of mass. This is a longer problem. If you can do this and understand how this works, the shorter ones are going to be super easy for you, okay? But this is the process that it takes for you to follow the law of conservation of mass. You have to follow it. You can't just create and destroy energy and electrons and atoms. That's not cool, okay? You can't do that. So we got to make sure everything is balanced and happy. So we're balanced and happy. Now we can move on. Let's look at number 7. Number 7 on our sheet says, what is the mole ratio? Okay? Here is my mole. My coefficient tells me how much of this compound I have. I have 4 molecules of NaCl. Okay? I have 2 molecules of sulfuric acid. 1 molecule of MnO2. 2 of sodium sulfate, 1 here, 2 here, 1 here. You get the picture. Okay? So now I can do a ratio of these coefficients to help me figure some stuff out. This is how they do a lot of combining of chemicals in pharmacy. This is how they do a lot of combining of chemicals when they're trying to make solutions for things. They figure out, hey, how much of this do I have? And how can I compare that to something else that I have? Okay, so number 7 says, what's the mole ratio of sulfuric acid to sodium sulfate? Here's my sulfuric acid. Here's my sodium sulfate. What is my mole ratio going to be? 2 to 2, which reduces down to 1 to 1, right? That's a ratio. How many of this do I have compared to this? How many sulfuric acids do I have compared to sodium sulfates? 2 to 2, which reduces down to 1 to 1. Okay, look at number 8. What's the ratio of chlorine gas to manganese 4 oxide? Here's my chlorine gas. Here's my manganese 4 oxide. What's the ratio? What's the mole ratio here? I've got how many chlorine? 1. I've got how many manganese 4 oxide? 1 to 1 ratio. 1 to 1 ratio. And then it says, what is the mole ratio of sodium chloride to chlorine gas? Here's my sodium chloride. Here's my chlorine gas. What's the mole ratio going to be? 4 to 1. I've got, for every 4 molecules of NaCl, I'm going to end up with 1 molecule of chlorine gas. That's what that tells me. My ratio of how much sodium chloride I have compared to chlorine gas. Okay? That kind of makes some sense? A little bit of sense? Okay, here's what I want you to do. Flip the page. Flip the note page. 9 plus 3. Okay, now before we move on to the different types of reactions, we're going to start talking about one really, really important concept that you need to know. Remember way back when we talked about diatomic elements? Elements that like to combine with another atom of themselves? Okay, look at the top there where it says diatomic molecules. Those 7 right there are your most electronegative elements. Okay, they very readily bond with themselves to make a stable compound. Okay, so if you notice, we had this up here, Cl2. Why do I have it like Cl2? Because Cl2, chlorine, is a diatomic molecule. It's going to seek out other atoms of itself to help bond so that they can both become stable. So they have a single bond between each other. Chlorine exists like this, Cl2, all the time. So anytime you've got chlorine gas, you have to write it like this. Okay, so there's a little anagram right there for you. It's Hun and the halogens, like a cool band group, Hun and the halogens. H-O-N. H is your hydrogen, O is your oxygen, N is your nitrogen, and then those 4 halogens, fluorine, chlorine, bromine, iodine. That's how you can remember it if you need to. It's on the periodic table back there if you want to look. Hun and the halogens. Make sure you know those 7. Okay? Any questions? No questions? No? Okay, let's move on. Synthesis. Okay? There are 5 different types of reactions. We're going to learn about 2 of them today. Okay? A synthesis reaction. Remember way back when, like 20 minutes ago, when I set that magnesium on fire? With that oxygen? That is an example of a synthesis reaction. I took 2 parts, magnesium and oxygen, and I combined them together and made a product. That is what's called a synthesis reaction. So if you look underneath, synthesis, there is a base formula that you're always going to use. X plus Y yields XY. Okay? I'm going to put one thing in, I'm going to combine it with something else, and here's what I'm going to get at the end. Okay, so if you think about it, what I did was a synthesis reaction. Let's write my synthesis reaction. What did I do? What would be my X? I combined what? Magnesium with oxygen. But how do we write oxygen? O2. I combined them together. There's my X, there's my Y. And so what did I get at the end? Magnesium and oxygen combined together. Magnesium and oxygen combined together to make, this is magnesium oxide, right? A nice, lovely ionic compound where I combine a metal with a non-metal. and made an ionic compound. So magnesium donated electrons to oxygen. That's what's happening right here to make magnesium oxide. Okay, so let's balance this out. We have to balance every equation, remember, right? Balancing equations. Is magnesium oxide balanced? No? What's magnesium's charge? What's oxygen's charge? Are they balanced? It's -2. -2, we're in group 16, right? So this is balanced. MgO. Okay? Oh no, there's no 2 here. Okay, when we're talking diatomic, by itself only. By itself only. Okay, so now, is this whole thing balanced? How many oxygens do I have on the left-hand side? How many do I have on the right-hand side? Not balanced, right? So I gotta balance this. How am I gonna balance this? What's the easy way to do this? Put a 2 right here. Okay, how can I balance the rest of this out? Now my magnesium's unbalanced. Add a 2 here. Are we balanced and happy and done?
Yes.
Yes, you just did a synthesis reaction. You put magnesium and oxygen together, figured out if it was balanced, know that it's not, placed coefficients to understand what's going on. So, for every 2 magnesium atoms I have, I'm going to combine it with diatomic oxygen to make 2 atoms of magnesium oxide. That's what a synthesis reaction is. That is the written part of me doing this, me setting magnesium on fire. That's what that means. Okay? I synthesized, I combined 2 things together. Okay? So, here's what I want you to do. Number 1, barium metal reacts with nitrogen gas. Let's walk through this one together so that you can see what's actually going on here. Okay, so I see barium metal reacts with nitrogen gas. So I'm going to write barium. That's going to be my X here. And don't forget to put your blanks out front because we have to make sure that we balance this equation. And what does it say I'm combining it with? Nitrogen gas, right? Okay, so nitrogen gas is going to be my Y. But what is special about nitrogen?
Into.
It's a diatomic, so I have to put a subscript 2. Okay, so this is what I'm putting in to my reaction. What are these called? Reactants. Reactants. Okay, so my arrow says, hey, I combine these together. So what am I going to get at the end? Ba combined with M. Ba combined with M. Now, I have to balance my end product. Is this balanced? Is it? No? Let's balance it. What's barium's charge? +2. What's nitrogen's charge? -3. So I cross and drop. I get Ba3N2. This is why we went over oxidation numbers for like a year and a half, right? Okay, Ba3N2, barium nitride. So, is this balanced on both sides? No. Best part is this is super easy. Are my nitrogens balanced? Are my bariums balanced? How do I fix it? Add a 3 in front of barium. So that means in this reaction, I need 3 barium atoms combined with 1 molecule of diatomic nitrogen to give me 1 molecule of barium nitride, Ba3N2. Is this not exactly what we've been doing? It's exactly what we've been doing. Naming of compounds, balancing equations. Now we're just adding coefficients in. This is all application of everything we've done the last month. Okay? So there's your synthesis reaction. X and Y combine together to give me XY. That's a synthesis reaction. So I want you to do number 2. Aluminum reacts with sulfur. And sulfur is not just S in this problem. It tells you that it's S8. So there are 8 atoms of sulfur here together. So you're going to have to balance that one out. That one's going to be tough. A little tough. I'll leave this up here so you can kind of see what we did. be a little tough. Okay, let's look at this one up here. Okay, we've got aluminum, and it combines with sulfur, which is S8, to give me aluminum sulfide. Is this right? No. What is aluminum's charge? +3. What is sulfur's charge? -2. So I have to cross and drop. It is important that you know that. If you don't have that correct, your whole equation is going to become unbalanced and messed up. Okay? It's important you know your oxidation numbers to balance this out. So now, what are we going to do here? This is where it gets a little crazy. Okay, we can balance out aluminum pretty easily. How do we do that? Put a 2 here. But now we hit an impasse. How are we going to balance out sulfur here and sulfur here?
3 and
Hmm?
3 and
Ooh, how did you figure that out?
because if you multiply the 3 and 8.
Yes. These aren't going to balance. Okay? They're just not going to be able to balance very easily. Who remembers the least common multiple stuff, like way back when, probably in middle school? These have a least common multiple that's going to help them balance out. How do we get least common multiple? Who remembers?
Multiply them by each
Multiply
other.
these two together. 8 times 3 gives me 24. That's their least common multiple to try to get these to balance out. Okay, so I'm going to need to get to 24. How am I going to get to 24? What do I have to put here to get my sulfurs to 24?
8.
An 8. Okay, so how does that affect my aluminum? Now I've got 16 aluminum. How am I going to fix that? Yeah, so I'm going to put a 16 right here. And then my sulfur. What am I going to put here to balance this out? A 3. Okay? So sometimes the numbers aren't even, and they don't work out. That's when you have to figure out their least common multiple. This is the lowest these coefficients can possibly be. I can't make them any lower. They have to be whole numbers. Okay? I can't cut this in half and end up with 1.5 moles or molecules of S8. Doesn't work. This is the lowest these coefficients can possibly be to make this to balance out. Okay? So, the synthesis reaction is I take aluminum and I take S8, I combine them together, I get aluminum sulfide. Okay? The next one, number 3. See if you can do number 3. Chlorine gas and oxygen gas react to produce dichlorine heptoxide. Who remembers what hept is? 7. Hexa is 6. Hepta is 7. So see if you can do that one. Okay, let's look up here. Does anybody see anything wrong with this?
You have to put the O2 and the
Okay, so are chlorine and oxygen, are they diatomic molecules? Yes, they will bond with themselves to make themselves stable. Okay, so now we can work this problem. Okay, are my chlorines already balanced? Yeah, and by the way, this is a covalent compound. I don't have to cross and drop and do anything here, right? That's covalent. It tells me what it is. Okay, so my oxygens. How in the heck are my oxygens going to balance out? Remember that whole least common multiple thing we did like 3 minutes ago? We can do it again. Okay, what is their least common multiple going to be?
14.
14. So how am I going to be able to get that? What do I have to put as a coefficient to get my oxygen to 14? Put a 2. Excuse me, put a 2. Okay, so how can I balance my chlorine out? Put a 2 here. Okay, that gives me 4 chlorine, 4 chlorine. Now, to balance out my oxygen, I've got 14 oxygen. What can I put here?
7.
7. 2, 7, 2. So I've got 2 molecules of diatomic chlorine, 7 molecules of diatomic oxygen, and they create 2 molecules of dichlorine heptoxide. Okay? Those are synthesis reactions. Just like me burning these two together. I take magnesium, I introduce diatomic oxygen to it, boom, it gives me that nice white powdery stuff that's now burned onto my desk. Magnesium oxide, okay? Any questions on a synthesis reaction? Okay, the next part, look at the second type of reaction, a decomposition reaction. Okay, we had X plus Y yields XY for a synthesis reaction. We were combining two things together. A decomposition reaction, it's just like what you would think. We're decomposing something. We're breaking it down. It's the reverse of what we just did. I take some combination of something and I decompose it. I break it down into its individual parts. Hey, we're not going to do any decomp reactions in here because a lot of times they produce things that are explosive or poisonous. I don't want to die on a decomp reaction today. I'm like December. That's not cool. Okay? So let's look at number 4. Let's perform a decomposition reaction. A very common way to decompose something is to introduce an electric current to it. Okay, so an electric current is applied to molted, which is just melted, sodium nitride. So let's do that one together. Sodium nitride. What is sodium?
In
What is nitride?
in 2.
N. Okay, now, this is how it looks. Okay, is this balanced? Why not? What is sodium's oxidation number? Plus 1. What is nitrogen's oxidation number? -3. So to balance this, we have to cross and drop. I get Na3N. Okay, this is why it's important to know your oxidation numbers. You can't just haul off and say NaN and keep moving. Okay, so I'm decomposing this. I'm breaking it down into its individual parts. Its individual parts are sodium and what? Nitrogen. But how do we have to write it? As a diatomic. Like that. Only when it's by itself. So now we have to balance this out. Okay, well how in the world are we going to balance this out? Okay, let's do the nitrogens first. It's going to be easier that way. What can I do to balance my nitrogens out here? Add a 2 as a coefficient to my sodium nitride. Now we should be pretty easy to fix this. What am I going to have to do to balance this thing out? What do I need here? I've got 6 sodiums, right? So I need 6 sodiums. What can I put here? A 6. And I have a balanced decomposition reaction that shows me that if I have a combination of sodium and nitrogen together, I will decompose them down into this. 2 moles of sodium nitride break down into 6 moles of sodium and 1 mole of diatomic nitrogen. That's what that means. That's a decomp reaction. Okay? And then number 5. See if you can do number 5. An electric current is applied to aluminum oxide. So we apply electric current. We're going to take aluminum oxide. It's going to break down into its individual parts. So see if you can do that one by yourself. Okay, let's look up here. Somebody find 2 things that's wrong with this. Somebody raise their hand and tell me 1. There's something wrong.
It's not equal.
What's not equal? Aluminum oxide, how do I balance it out?
It's aluminum two.
Al2O3. Okay, so aluminum oxide has to be Al2O3 because aluminum has a +3 charge, oxygen has a -2 charge. You cross and drop them to make this balance. What else is wrong? Something else is wrong. Kyle?
Oxygen needs to be O2.
Yes, oxygen has to be O2. Very easy to forget that as you're going through this. Okay, now, how are we going to balance this? Okay, let's start off with the easy one. Balance aluminum. Let's balance it. We'll put a 2 here, right? Okay, well, that stinks. Now, how are we going to balance this?
Put a 3 and 2.
Can we put a 3 and a 2? Why? Because we have to find the what? Least common multiple. What's their least common multiple for this oxygen? 6. So how do I get 6 oxygen here? Put a 2, which means I have to change my aluminum to what? 4. Good. And then my oxygen here to get to 6, what do? 3. So these are my coefficients telling me I need 2 moles of aluminum oxide to produce 4 moles of aluminum and 3 moles of diatomic oxygen. Okay? That's how this process works. It can be time consuming, but if you know how to name compounds, you know how to balance compounds, your life is going to be very, very easy. If not, it's only going to get more difficult from here. Okay? These are the 2 reactions I want us to learn today. Tomorrow we're going to get into single replacement, double replacement, and then we're going to balance the heck out of some equations. Okay? Good work today. We are done learning for today. Not forever, but for today. Now, let's talk.